Hello guys, and welcome to my YouTube channel. In this video, we will be discussing enolates. This video is going to be broken down into two parts. Part 1, we will discuss how to form an enolate ion. And in part 2, we will discuss what happens between an enolate ion when it reacts with, for example, another aldehyde, like in this question. So we have part 1. And we have part 2. Now for part 1, we can break it down into 4 general steps. Step 1, I always want you to refer back to these steps when you're in doubt, when you're trying to solve one of these problems. Step 1 is finding the acidic hydrogen. We will refer to this hydrogen as the alpha hydrogen. Step 2 is to form that enolate ion. Step 3 is to attack the carbon of the carbonyl of the aldehyde. And then step 4 would be to form your product. So I just want you to refer back to these steps whenever you're in doubt as we're moving through these problems. So let's go over our first example. So we're focusing in on step number 1. The first thing you must do is identify the carbonyl carbon and identify the base. So here, this would be the carbonyl carbon, and the OH would be the base. These are 2 things that you need in order to perform this reaction. So once you've identified the carbon, a part of the carbonyl, well, now I want you to identify the carbons that are directly attached to that carbon. So who is holding hands with the blue carbon? Well, this carbon is holding hands with the blue carbon. If that carbon is holding hands, meaning directly beside that carbon, well, we're going to call this the alpha carbon. So the carbon 2 carbons away would be the beta carbon. And now say it with me, okay, if that's the alpha carbon, well, what do we think we're going to call the hydrogens that are attached to that carbon? And this carbon, since it already has 2 bonds, carbon-carbon bonds, well, we need to draw in 2 hydrogens because every carbon makes 4 bonds. We're going to call these green hydrogens the alpha hydrogens. And if you remember what I said about the general steps, well, step 1 is identifying that alpha hydrogen. Yay, we did step 1. So if the pink carbon is referred to as the beta carbon, well, what would we call the hydrogens attached to it? Well, we would call them the beta hydrogens, exactly. And say it with me, how many hydrogens would we have to draw in for the pink carbon? Well, we would have to draw in 3 hydrogens this time because every carbon must make 4 bonds, and right now the pink carbon is only bonded to the green carbon, so that's only 1 bond. So we would need to draw in 3 more bonds. I'm going to erase this to make it look a little bit cleaner. And right now we do not care about the beta hydrogens, so I'm just going to draw in the alpha hydrogens. So this is H alpha 1, let's say. I'm not going to draw in H alpha 2 because we don't really care about it right now. This base is only going to go and grab 1 hydrogen. So what's step number 2? Step number 2 is forming the enolate ion. How do you form the enolate ion? Well, hydrogen alpha 1 must be stolen by the base. So whenever you have Na paired with anything, it is positively charged, the other thing is negatively charged, and you can pretty much forget the Na exists. So we know this oxygen has a negative charge. Draw on its lone pairs. So what is it going to do if it's nucleophilic, hence nucleus loving? Well, it's going to attack something that is delta plus, for example, an acidic hydrogen. So it is going to go to steal this hydrogen. And then the 2 electrons in the carbon-hydrogen bond are going to go 2 up onto the alpha carbon. Now, if you gain electrons, you become negatively charged, referring to gain electrons become negatively charged. So the alpha carbon is now going to be anionic, negatively charged. Carbons with negative charges are very unstable because carbon is not electronegative. So this negative charge is searching for somewhere else to go. And the electrons want to travel towards atoms that are more electronegative. So who's more electronegative than a carbon? Well, an oxygen is, right? So the electrons want to travel towards this oxygen. The real question is can we draw a resonance structure that puts this negative charge on the oxygen atom? And the answer would be yes. We could go 2 over, and then the 2 electrons in the carbon-oxygen bond would go 2 up. So let's draw the product of pushing these 2 arrows. So now the oxygen, if I draw in the lone pairs that were originally there, let's say we draw them in blue, the oxygen would gain these 2 green electrons, so it would become negatively charged. Gain electrons become negative. And now the negative charge, these 2 electrons, they moved in between the alpha carbon and the carbonyl carbon. We gain a bond in between the green and the blue carbon. And this would be our resonance structure. And this is also our enolate ion. That's it, guys. That is how you form the enolate ion. So this is everything you need to know for step 1. Step number 1 is completed. This is how you form an enolate ion. So what is the summary? Step 1 is you want to put a negative charge on the alpha carbon. And then step 2 is you need to draw a resonance structure that puts the negative charge on that oxygen atom, because this is a more stable intermediate, because oxygen is more electronegative than carbon. So now let's move on to step number 2. The product of step number 1, after we deprotonated the alpha carbon, well, the alpha carbon becomes negatively charged, so anionic. And then we draw our resonance structure. So the negative charge ends up on the oxygen atom, which is more electronegative than the carbon. So now question is if I have this guy and I have this guy, let's say 50% of the time, right? Because resonance is meaning sometimes I look like you, but other times I look like you. But more often I look like you because this is the more stable structure. And I want to remind you of a trend. If you increase stability, what does this do to reactivity? Well, think if you had a dog, right? And this dog just chilled all the time. It did pretty much nothing. When you left the house, you wouldn't be worried about it ripping up your couch, right? But let's say you got a rescue dog and you hadn't trained it yet. You might be a little worried about leaving it to roam free in your house when you leave, because maybe it'll tear up your couch. So you're probably going to put it in a cage, right? So increase stability, put it in a cage for when you leave your house. Obviously, then when you get home, you're going to cuddle your puppy. So then when you increase the stability, well, that's going to decrease the reactivity. If you have a stable dog, it's not going to rip up your couch. But we also have the opposite trend, right? If you decrease the stability, well, what do you do to the reactivity? You increase the reactivity. So, how do you become reactive in organic chemistry? Well, to be reactive, you need to have a negative charge, right? And both of these structures, let's say structure number 1 and structure number 2, they both have an atom with a negative charge. Let's draw it in red. So this carbon is negatively charged in structure number 1, and in structure number 2, the oxygen is negatively charged. So let's say we throw in something that could potentially be electrophilic, right? So we're going to throw in this aldehyde. The question is, which atom reacts? The electrophilic center is going to be the carbonyl carbon on the aldehyde. So let's draw it in purple. This is going to be your delta plus center that is going to be attacked by some nucleophilic atom. But the question is, well, does this atom do the attacking? Or does this atom do the attacking? The answer lies within this trend. Which atom, which negatively charged atom, so which red atom, is more unstable, hence more reactive? Is a carbon anion or an oxygen anion more reactive? I hope you say it's the carbon, because carbon hates having negative charges. Yes. So that means when we go to actually react, well, these 2 electrons are going to come back down, and the carbon is actually going to be the attacker. So let's redraw this, and we'll do this step by step, keeping everything we have just discussed in mind. So we form our enolate ion, okay? But then we toss in an electrophile. We want to attack this really yummy delta plus carbon, right? Because opposites attract. First, we must go back to our unstable intermediate, 2 and 2 up. So draw the resonance structure going back to what you originally had. Negative charge. And now that the negative charge is on the more unstable atom, now this carbon will go 2 in, 2 up. And now we can draw our product of the reaction between an enolate ion and an aldehyde. This is also referred to as the aldol addition product. What I recommend you do is on each substrate, let's label the carbons. Here I'm going to label them in green. 1, 2, 3 carbons in green. 1, 2, 3. And then we'll label the carbons on the other structure in blue. 1, 2. So make sure you do not draw any more carbons than 5 carbons because you initially had 5 carbons total. 3 plus 2 is 5. So in your product, you must also have 5 carbons. So I'm going to start off by drawing the green ones, okay? Draw the green structure. And then I'm going to draw in, labeling them 1, 2, 3. Starting at the red carbon, because that's the carbon that did the attacking, carbon number 2, I'm going to draw one line, okay? Every time you draw an arrow from an atom that is negatively charged, you're just drawing a new line. That's a new bond that formed. Who did it form between? Well, it attacked carbon number 2 on the other structure. And carbon number 2 is attached to carbon number 1. And carbon number 2 also has a bond to an oxygen, but that oxygen is now negatively charged because the 2 electrons initially in that pi flicked upwards. So this would be your structure, or your intermediate thereof. So now how do we finish this reaction off? Well, all you got to do is work it up. And what does work up really mean at the end of the day? All it means is you add a hydrogen to the things that need them. So who needs a hydrogen right now? Well, the negatively charged atom does. So your final product, all it would be is erase the negative charge and draw in a hydrogen. That would be your final product. And usually we're going to draw this in a bit different way. This is just the easiest way to actually get the structure right. Essentially, you want to draw all the carbons, a part of both of those chains, in a zigzag formation going, let's say, across the page. So that's why we have carbon 1 to carbon 2 with our bond to an OH, then the red bond that was formed, and then we have carbons number 1, 2, and then 3 with our double bond O and our aldehyde. And this is our final structure. Alright guys, thank you for watching this video. Please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. And I hope that you find my videos helpful and watch the other ones. And yeah, leave a like, comment, save, and or subscribe. I'd love to hear your guys' feedback. And yeah, I really hope this video was helpful. Before I leave, I'll just quickly draw a summary. So after this step, the intermediate where the negative charge is on the unstable alpha carbon. And then this guy reacts with this carbonyl carbon, 2 and 2 up. And then we get our final product, which forms in between the enolate ion and the aldehyde, where if we're going over an addition reaction, we just get an OH group at the end. So in summary, we end up with the carbonyl carbon, and it is 1 carbon away from the carbon with the OH group. This would be the product of your addition reaction, where an enolate ion reacts with an aldehyde. Bada bing, bada boom.